Hey everyone, welcome back. Today we're going to talk about Exploration 2. This is from Unit D, Lesson 1, Exploration 2. I'm on page 11 in your books. And so this exploration is about studying the age of fossils, determining how we determine the age of fossils, and we're going to determine what's called the relative age and kind of the absolute age, the real age of fossils. Okay, so some of the struggle with fossils is no one was around to see them forming. Fossils are old enough, it's not believed that humans were on Earth when fossils formed. So we're talking millions of years for fossils and thousands of years for humans. And so scientists, they assume that the geologic events on Earth that happen today also happened in the past as well. So they happened in the same way. So it's kind of the exact same. We call that uniformitarianism. Okay, that's what that process is called. So for example, sedimentary rock. Sedimentary rock forms from sediments. And so what happens is Earth can get eroded and forms layers, and then over time those layers get compacted into rock. Okay, so you can see from the picture here, this is from a river here, this kind of lighter area, those are sediments that are getting carried out from the erosion of the land into the ocean. So those are the sediments that are getting carried out. Erosion is one way we can get those sediments to form. And so how does the knowledge of sedimentary rock formation help us to understand fossils? And well, the answer is knowing how the rock around a fossil is formed helps scientists draw conclusions. They can learn about the environment the organism lived in. They can see some of the other fossils that are with that organism, so they can see maybe some of the things that organism ate, or maybe what other organisms lived at the same time period. Okay, so what we can do with these sedimentary rock and these layers that form is we can get what's called the relative age of rocks. Okay, so if you look at the picture of the Grand Canyon over here, you can see, and maybe some of you guys have been to the Grand Canyon and you've seen this in person, or you can see it is like in the side of a road that cuts through the side of a hill, and you can look at the side of the hill and you can see these rocks, these layers of rocks. Okay, so each one of these layers would be a layer of sedimentary rock. And so the oldest layers are at the bottom, the youngest layers are at the top. That's kind of common sense, right? So the rock layer at the top of the Grand Canyon is the youngest because it was deposited the most recently deposited. Okay, the layers in the middle are younger, or the middle are older than the surface layer, and the furthest down are the oldest. Okay, because it was deposited the earliest. So the further we go down, the older they are. So we know we found a fossil that's in the middle. It is older than if we found a fossil that's up towards the top. And if we found one at the bottom, that's going to be the oldest type of fossil. So that organism lived before the other ones did. Okay? So that forms what's called geologic columns. Okay? So scientists compare the relative ages of rocks in different areas by the columns. Okay? That's what we can do. So geologic columns are models that are used to organize the Earth's geologic history and fossil record. How do they relate to the principle of uniformitarianism? Well, the phenomena that occurred in the past still happen today. So erosion that occurs today, it also happened in the past as well. Gravity, tectonic movements, the plates, tectonic plates movement. You guys talked about that last year in the 6th grade. So geologic columns are based on past geologic processes occurring in similar ways today. So we kind of just believe that what happens today also probably happened in the past as well, in kind of the same way. Now, to determine the absolute ages of rock layers, so absolute means kind of like how old they are in years. The layers, so if we look at that Grand Canyon, we can only tell that something in the middle, one of the layers in the middle here, is older than what's at the top. Okay, and at the bottom is older than what's at the middle. But we can't tell how old they are in years, like how many millions of years old this rock is compared to this rock at the top. We don't know. And so that's where the absolute ages of rocks comes in. And to do that, we do something called radiometric dating. Okay, we do something called radiometric dating. And what it does is certain elements in Earth are radioactive. And what happens with radioactive elements is that they decay. In other words, they change from one element into a different type of element. Okay, so for example, uranium is an example of an element that can be radioactive. And the radioactive uranium, over time, actually turns into a different element of lead. And so if we have a brand new rock, it has this uranium in here. Okay, but over time, that uranium and that brand new formation of formed rock, this is like from a volcano. So like if a volcano erupted, it creates new rock on Earth's surface. It has this uranium in it. And over time, that uranium actually turns into lead. And it's something called a half-life. It's a standard kind of formula that scientists can use. Okay? And so for uranium, a half-life is 704 million years. That means if we were to have a brand new eruption today of a volcano that creates this rock, and it has this uranium in it. If we were to have a time machine and go into the future, 704 million years into the future, half of the uranium that was here would now be turned into lead. So we have half of the uranium is still there, and half of it is now lead. And so we can measure that. Scientists can measure the amount of lead versus the amount of uranium that's in a rock, and then can calculate how old that rock is. Okay, and so each half-life, so then if we go 704 million years again into the future, half of the uranium that was there is now turned into lead. And if we go again, another half is now turned into lead. And so scientists can calculate that, and that's called radiometric dating. So that process of calculating the amount of radioactive materials is called radiometric dating. So a fossil, if we have a fossil that's found in the sedimentary rock layer, the igneous layer directly above the sedimentary rock layer was analyzed for radioactive uranium. You found equal amounts of uranium and lead in the igneous sample. This means that the absolute age, because the absolute means we can actually get a year on it, how many millions of years old it is. The absolute age of the igneous layer is 704 million years old. And the age of the fossil and the sedimentary layer is older than 704 million years, because if it's below, it's going to be older, right? And so we know that it's a little bit older than 704 million years. Maybe we can get, there's another igneous rock layer below it that's, we could say, 800 million years old. And so then we can maybe say, well, this layer right here, we can get within about 100 million years of how old it is at that point. Okay? The other things that scientists use to determine the age of fossils is called index fossils. Okay, so index fossils are fossils that appear only in a certain layer of rock on Earth. And so these index fossils maybe occur in many places around Earth. Okay, so lots of places around Earth. It's an organism that lived in a lot of different places around the Earth, but these fossils only appear in a certain layer. So they don't appear in more than one layer. It was just a particular time in Earth's history where these fossils lived. And these are called index fossils. And so if we find one of these fossils with a fossil of a new organism, so a previously undiscovered organism, but they're in the same layer, we basically know how old that organism is because we know how old these index fossils are. So if they're found together, we can determine how old a fossil is. Okay, so this is an example of one. This is a extinct sea snail. They were alive in the late Jurassic period. Okay, they're what's called the index fossils for the Jurassic period. All right, so when we determine the age of fossils, okay, so different fossils occur in different places around the world sometimes. So we can look at this, and so we can see the different locations here. When some of the fossils are the same, so some of the fossils are the same in those different locations. Okay, but if we know, like here is an index fossil, this particular type of fossil only occurred in one layer of rock all around the world. It's the only place we've ever found it. And so if we find other fossils in that layer, we know how old those other fossils are. Okay, or sometimes we have igneous rock, so we can date this igneous rock like it's a lava flow that would maybe occurred here. And so if we know how old this is, we know maybe we can get an idea of how old the layers above and below it are as well. Okay, so suppose the index fossils in the diagram has an absolute age of 454 million years. So if we were to write in our own words and explain how scientists could estimate the ages of the other fossils in the diagram based on the information, well, one example could be the use of index fossils and absolute dating of the igneous rock layers can then relatively date the other fossils in the other rock layers. Okay, so if we know how old this fossil is in this rock layer, we can then say that, well, these fossils are older and this fossil is younger. Okay, or if we know how old this layer is right here, we can say that these fossils down below are older and these fossils above are younger. Okay, and so if we put all of that information together, we can then get the geologic time scale. Okay, so the geologic time scale is kind of the history of life on Earth. We believe that the Earth is about 4.5 billion years old, and to help make sense of this vast amount of time, we can use what's called a time scale. And sometimes you do this in social studies as well. You'll make a time scale in social studies over a certain period in history. Okay, so we can divide the time scale up into different periods and different eras. So maybe you've seen the dinosaurs. They were actually from the Cretaceous era. Okay, not actually the Jurassic. They weren't actually. So if you ever see Jurassic Park, that was actually not the era that dinosaurs were from. They're actually from the Cretaceous. Steven Spielberg, who directed the Jurassic Park, he just thought Jurassic Park sounded better than Cretaceous Park, so he named the movie Jurassic Park. So, if we were to do the math here, the geologic time on Earth spans more than 4.5 billion years. So if we were to put that out on a football field, which means starting at one goal line would be year 0, and at the other 100 yards down the field, the other goal line would be 4.5 billion years later. Okay, so if we were to use the data there, Earth's history on each yard line, so we take 4.5 billion divided by 100, we would actually get each yard would represent 45 million years. Okay, so the first modern humans appeared on Earth about 200,000 years ago. We believe the humans appeared on Earth about 200,000 years ago. Would it be possible to measure that number in terms of feet on the football field? And the answer is no, because 200,000, if each yard is 45 million years, 200,000 compared to 45 million, 200,000 isn't all that much. So the distance would be far too small to measure or mark, even on a football field. So that's the idea of humans on Earth. It's the amount of time that Earth has existed and life on Earth compared to the amount of time humans are believed to have been here is very small. And so we're still trying to understand a lot of things, that's for sure. All right. So page 16 here, last page of this exploration. Number 16, that refers to the phenomenon from the beginning, the picture of the whale and the whale skeleton there. So the whales lived during the late period here. I don't even know how to pronounce that one actually. Where does that fall on the geologic time scale? How might the time in which the whale was alive have been determined? And so if we record our evidence here, well, it was about 40 million years ago. And it was found through a combination of what we call absolute and relative dating. We actually date the rock and then determine which layers above or below are older or younger. Okay, so we can estimate the ages of fossils. Like we have this turtle here, this fossilized sea turtle. It has bite marks on its shell, indicating that it was in a predator-prey relationship with another sea creature for sure. And then if we found this sea turtle in an area where we also found some other index fossils, like these other sea creatures here, what methods could we use to help estimate the age of the turtle fossil? Well, we could date the fossil with the relative dating method. So if we find a layer of rock above or below that we know how old it is, we might know how old that turtle is, or if we know how old these organisms are and they're found in the same layer, we know how old that turtle is about. We could look up the age of these index fossils, okay, and we could date nearby igneous rock layers, new rock formation layers, and we're using radiometric dating, and then we could find the age of that fossil. So there's lots of different ways we determine the age of fossils, and we're going to talk more about these as we progress in this lesson. All right, good job, guys. That's the end of exploration 2. We all got one more exploration for this lesson. Thanks for all the hard work.